long.
So this is helpful because actually kind of clears it up because we do some of the stuff in here that's a little more solidified.
Yeah. I'm guilty of, I kind of go overboard on the proofs, or I have historically.
Definitely not.
I'm trying to dial it back.
So compared to the other stuff.
So this is good. I'm glad.
Helpful.
To hear you
It's so
say
funny comparing like what we do in math, like proving a theorem to like physics, because them is like postulates.
Yeah.
Going on with.
Yeah.
It's like we just talked about the uniqueness theorems, you know. And it's like, yeah, they're true.
What do you have for you? You fake it?
Fake beat.
I had them last semester. I loved it.
And then we're doing a bunch of not doing anything, but like.
Oh, okay. So let's start. So remember at the end of Tuesday. Oh, I'm sorry. I should make some announcements first. We have something of an embarrassment of riches here. I wasn't able to bring myself to choose problems to give you a practice final. It's just too many problems. I know this is my own decision paralysis. So I'll ask this on Canvas over the weekend. Would you rather have the exam postponed to the following Tuesday?
Chance.
Or
Personally, yes. I have a midterm that Thursday and another one on Friday.
Actually, I'm gonna stick with that. Yeah, I have a lot of stuff next week.
okay, so I'm looking at some
I have a midterm that Monday.
So that would be the second. November 2nd.
November 2nd. Yeah, that's right.
Yeah, that's fine.
Would that be okay? Okay, so I'll make sure. As long as that's okay with and
Is Sam on the first or second?
then maybe you know, like we're pretty freeform here, right? Like it's just the 8 of us all together.
Yeah, that midterm will be easy, guys.
So you know, we could even push it back an entire week, right? That's also fine with me. I don't really mind. In fact, I kind of like that better because we'll be able to do some. We're right at the precipice of proving some really powerful facts about integration of complex functions. Okay, so if we pushed the midterm back an entire week, we could have a lot more interesting, not necessarily more difficult, but more interesting questions on the midterm.
Good with that.
Okay, I'll just to confirm, I'll send out a questionnaire over Canvas, just to make sure, you know, we have a couple people not here, so I want their input too. Yeah, let's just keep in mind that maybe the midterm will be pushed back a bit. I hope that's okay with everybody. And what I mean by that is, I'm sorry that I wasn't able to get it together, give you some practice exam. Just I don't know what it is. I can't decide what problems to ask you. Oh, right, and also I made an announcement on Canvas about the midterm evaluations. I would like you all to take a couple minutes and just give me some feedback. You know, tell me what's working. I know that some of you have filled it out already. Of course, I don't know who. It's anonymous, but if you haven't, please do take just a couple minutes over the weekend. You know, give me some feedback. Tell me what to do differently or better or something. Okay. Okay. So remember, we left off on Tuesday defining the principal value of the complex logarithm in the following way. Oops, sorry. So right, I'm overloading this notation, capital log. See, here it has a complex input, and I'm saying that when I have a capital L with a complex input, I mean the principal value of log, right? Where we take the principal value of the argument. And here, by capital log, I mean the natural log of a real number, the modulus of z. Capital R of z, right? And I claimed that this function is analytic in d star and satisfies d dz of log of z is equal to 1 over z. The usual differentiation rule for the natural logarithm in real numbers. Okay? And what do I mean by d star? I mean the plane minus this branch. I take this line of discontinuities, right? Since I take the principal value of the argument, this means that the argument is discontinuous as we get to pi, right? And then we jump down to negative pi instead of going to pi plus epsilon. Right, so the principal value of the complex log has the same discontinuities. So let's give an idea of the proof here. So let's first set w equal to log of z, and we wish to show for z naught in d star and of course we'll just say that there's some w naught, right? Is the value of log at z naught. We wish to show that the following limit, the limit as z approaches z naught of w minus w naught divided by z minus z naught exists and equals 1 over z naught, right? Just reconciling the definition of derivative with what we claimed it was, the usual thing from the real function, natural log. Okay, so how should we go about this? Call since the function z equals e to the w is analytic, we have that the limit as w approaches w naught of z minus z naught divided by w minus w naught is equal to dz dw evaluated at w naught, right? That is to say, since I'm analytic, I know that this limit exists, i.e. I'm differentiable at, in fact, this is not just analytic, but entire for any point, w naught. This is, this is the case. So this is just equal to e to the w naught, which is equal to z naught. Okay? Because remember now here I'm working with the principal value of log. It's capital L. So I can say this equation holds. It's not plus 2 pi k I for integer k. Okay? Good. So, in other words, so we'll be done if we show I'll call this equation star, the limit as z approaches z naught of w minus w naught divided by z minus z naught, which of course, oh sorry, not of course, if we show that this limit is equal to the limit as w approaches w naught of 1 divided by this difference quotient flipped. Okay, so that is to say, if we show this equation is true, this equality of limits, then we'll be done. Right? Okay, so how do we go about this? Okay, so what we do, that is to say, we'll be done since we know, we already know how to evaluate the right-hand side of this, right? The limit as w approaches w naught of 1 over v minus v naught divided by w minus w naught is equal to 1 over z naught, right? Because we computed this limit already. Or rather, we didn't compute this limit, but we know it exists and it equals 1 over z. Right? We said this correctly? Yeah. Right. Yeah.
Just a quick thing. So if you rationalize, if you rationalize the limit, you get w minus w naught over z minus z naught on the right side, right?
On the right hand side?
Yeah.
Yeah.
But wouldn't that limit just be 0? As w goes to w naught, you get w naught minus w naught? Or can you not say that because z has dependence on w?
Because, say that again.
Because z has dependence on w.
Yeah, right, so that's what it comes from, that we have this from the outset.
Yeah, right.
Okay, that's actually the next step that we'll see here. Okay, so yeah, so let's write that on the board. The equality star follows from the fact that as we said, I don't think I said this at the beginning of class today, but at the end of class on Tuesday, we hopefully convinced ourselves that log of z is continuous in d star, right? It's continuous away from, I erased this, maybe I should have left it here, but it's continuous at every point that's not on the negative real axis, right? Just as capital R of z is. Okay, and so, as z approaches z naught, w must approach w naught. Okay? W naught. Right? Okay. Why is this? Since otherwise, Z equals Z naught as e to the Z equals W, right? That is to say, as we're approaching, as long as we don't get exactly to W naught, we're not going to attain W naught beforehand, before we get there. Okay? Okay, so great. Log Z is as analytic as we can possibly make it. Right? It necessarily depends on some choice of branch cut. But what we can tell right away from this, let's tie this back into what we were talking about before we started talking about elementary functions. Here's a corollary. What does this tell us? Capital arg Z is harmonic in D star. That's probably useful to us. And furthermore, the natural log of the modulus of Z, which of course is the real function. Now, I hate this, but I got to side with the book on this one. This is pretty universal. You just have to pay attention to what the argument, I'm sorry, I shouldn't say argument, what the input is to capital log, right? And here I'm talking about the real valued function, the real function, right? Because I'm putting in the modulus of Z, the real number. But I'll try to remember to say that for emphasis whenever it comes up, because it does get confusing. I admit that, but this is everywhere. There's not a better convention for this, fortunately. So the real function, log of modulus of Z, is harmonic in the, what we usually call the punctured plane. i.e. C minus the origin. Okay? Right. So, good. Now let me ask you some practical questions here. Now that we have these properties of this elementary function. I mean, you know, it's perhaps a little misleading to call log an elementary function since it depends on a choice of branch cut. That seems kind of complicated. But the name is a holdover from the real function, right? It's the inverse of something that is very important to us, the exponential function. So, it gets in the club of elementary functions. Okay? So, let me ask you to try the following problem. I'll take a couple minutes on this independently. Determine the domain of analyticity for the function f of z is equal to log of 3z minus I. And let me also ask you to compute f prime of z. Oh yeah, let's just take 2 minutes, try to work this out, and then we'll come together and talk about it. I get a drink of water, I'll be right back. So what do we think? If anything, I'm sure you guys think something. What are our steps to find the domain of analyticity for this function? Okay. Yeah.
Well, the way I started was I considered so log of z is analytic everywhere except the negative real axis.
And 0, but yeah.
Yeah, 0. So that means that the argument, so the input
Yeah.
has to be cannot correspond to that axis in 0. So that means that the input has to be in the form, or it has to be equal. It's not analytic for an input equal to the form of negative a, where a is a real number.
Right. Okay. So, yeah, that's pretty much on the right track there. Yeah. Let's say let's record some things here. Okay. So 3z minus I cannot be a non-positive real number. Okay, so in other words, what am I saying by saying this? This is implies, well, 3z minus I is negative and real, or sorry, non-positive. It's an unnatural thing to say. Non-positive and real, where on the ray, where x is less than or equal to 0, and y is equal to 1/3. Where, of course, I'm using my standard convention here, that z is equal to I plus x plus iy. Right? So, just pictorially. Just looking. I'm analytic. That is to say, f of z is analytic everywhere except this red. And I've just shifted where I took my branch cut, basically. Right? Okay. Good.
It's still valid to do that algebraically.
Say again?
So it's valid to do that algebraically, right? Like 3z minus 1 equals a complex number that is only a negative real component.
Yeah, exactly.
Solve for z.
Mm-hmm. Yep. I skipped the algebra here, but yeah, that's how you would deduce this. Yeah. Sorry, I just feel like I really hit you hard with a lot of computations over the past couple of weeks. Trying to cut down on some of that. I find it boring. I don't know if you. What do we think? Is that should I show more algebra? Should I show more computations, or is this okay?
I mean, for stuff like this, I think just like
Yeah, this stuff is
geographically, it makes a lot of sense. If it's like,
Okay.
if it doesn't, here's like simply geographically, the algebra would be nice.
Yeah. I mean, like when we did the partial fractions thing, I
Yeah,
know
that
that was
was-
painful, but I feel like that was
That
natural.
was
helpful.
bad, yeah.
That was very
Yeah.
helpful.
Okay, good. As long as we're on the same page. Good.
the invisible stuff is also a lot of algebra.
Say again.
Like the invisible stuff.
Oh, yeah, right. That's what I mean. Like, I feel like we've been doing. That's not why you come to class to see me make a bunch of computations and make a lot of mistakes, right, which I'm prone to do. So, try to cut that out whenever I can, and hope that you all will point out when I do things wrong, or if I do things wrong in the notes, then you'll call me on it. I'm relying on all of you for that. Okay, so right. I should say we often call this the slit plane, or a slit plane. Taking a piece of paper and just cutting the scissors halfway into it. Okay, so as for computing f prime of z, remember we proved this whole laundry list of regular rules for differentiation. We just used the chain rule like normal. Now that we proved that the derivative of the complex function log of z is just 1 over z, we can apply the chain rule like normal. Okay, so that is to say, f prime of z is just 1 over 3z minus I times straightforward, right? Okay. So again, let's revisit some terminology, and again, I'm going to do some overloading here. I'll assign several meanings to the same word, but hopefully it will be clear from context which meaning I'm applying. So, f of z is said to be a branch multiple value function f of z in domain D if capital F of z is single valued, that is to say, capital F of z is a function as we have classically conceived of them, just like always, right? A function is supposed to have just a single value. This weird thing, this multiple value function. And we choose a branch of it, which is a restriction, a new function, which is a restriction of the domain. Right? So the overloading here is that we had called the domain restriction a branch when we talked about argument. Now we're actually specifying this function that we get from restricting the domain is the branch. It's a very slight overloading, but still technically two different things. So right, if f of z is single valued and continuous in D and for any complex number z in D, f of z is one of the values of little f of z. Okay, so there was this problem that I really wanted to include on the problem set, but I felt like it was getting too long, so I didn't. But I'll pose it to you all today while we're here, and maybe just think about it over the weekend. No pressure. You don't have to turn it in or anything. But yeah, we'll get there shortly.
Saying f of uppercase f of z is single valued, is that another restatement of uppercase f of z is injective?
No. All I'm saying here is that f of z, capital F of z,
Returns one value.
is a function in our usual sense of function, that it only returns one value. Right? So yeah, it's kind of a certain type of opposite of injective. Right? Usually we exclude the notion of multiple value from our notion of what a function is. But because we want to invert these non-injective functions in the complex domain, we want to consider these multiple valued functions, which are pathological things, but they're actually kind of useful. And like I showed you for the argument of multiple valued function, result in interesting topology, right? This twisty sheet, for example, which perhaps not surprisingly is called a Riemann surface. And there's a whole class of surfaces that you study in more advanced differential geometry that have this same type of property as the twisty sheet we saw for the argument of z. Okay? Right, but we won't be too concerned about those things. Maybe a little concerned, but not too concerned. Okay, so let me just say, when convenient, slash necessary, we may choose a different branch of lowercase log of z, right? This multiple value function. And we have notation for this, right? Because it does actually come in handy sometimes to choose a different branch. script L sub tau of z is almost identical to the principal branch of lowercase log of z. We take the natural log of the modulus of z, the real function, plus I times the arg sub tau of z, right? And remember, arg sub tau of z has domain tau, comma, tau plus 2 pi, right?
Would the tau plus 2 pi be closed?
Yeah,
Okay.
sorry. I was saying that to myself in my head, but I failed to write it. Yeah, so you were close on the far end, right? Okay. So here, the branch cut is the ray in polar coordinates. Theta is equal to tau, right? With this domain. So that is to say, another way of saying this is that you can never make a branch cut to define a branch of lowercase log of z that is continuous in any neighborhood of 0. Right? You're always going to be a ray out of the origin is where your branch cut is going to be. Anywhere you want, you can choose any tau you like, but you're not going to be able to find a neighborhood of the origin where the branch that you chose, L sub tau of z, is analytic everywhere in that neighborhood. Right? You're always going to have a ray emanating from the origin. Or perhaps I've misstated something here. This is related to this problem. Your branch cut does not have to be a line. You can actually make your branch cut any curve that intersects the origin. Okay? So, here's this problem that I wanted to include but didn't. Think about this. How would I construct a branch of lowercase log of z, with branch cut y equals the square root of x. That is to say, pictorially, this is a valid branch cut. Okay, and furthermore, let's call this L sub P for parabola of z. What is the derivative here? And it should be something related to 1 over z somehow. But how do we factor in for this parabolic branch cut? This is a fun thing to think about. So that's all I'm gonna say. Just think about this, and maybe we'll discuss it some on Tuesday. Okay? But again, no pressure. Yeah, I know the problem set is already kind of long. That's why I didn't include it. But this is fun.
So you can take a branch cut of any arbitrary curve.
That terminates in the origin.
So you could do like some weird kind of.
Well, I shouldn't say
polynomial curve.
any curve. I should say at least like
Yeah.
continuously differentiable or something like that. I actually don't know the answer to that off the top of my head. What's the most general curve you can have terminate in the origin and be a branch cut? That's an extension of this problem. That problem isn't in the book, but it's a good question.
I'm thinking like a circle that has one end that terminates in the origin. Not like a true circle, but like a circle with like a divot that starts and ends in the origin.
Well, I think no matter what, you're gonna have to have a your branch cut has to be unbounded to go out forever. So that's probably another thing you could say. I'm actually not sure the answer to that in general, but maybe let's all think about that over the weekend. Okay. So all that aside, let me ask you perhaps an easier question. Let's try to determine a branch of f of z equal to the lowercase log of z cubed minus 2 analytic at z equals 0, and let's try to find find f of 0 and f prime of 0. I guess I skipped a step here, right? Find a branch of f of z, call it capital F of z, right? And then find the values of capital F of z, capital F of 0 and capital F prime of 0. Okay, so, what do we do here? So, what are we even looking for? Let's first of all just note that the multiple valued function lowercase log is composed with this function g of z is equal to z cubed minus 2, right? Is the composed function. Okay. So we need a branch analytic at g of 0, which is just 0 cubed minus 2, or minus 2, right? In other words, I ask you to find a branch of this function f, which is analytic at 0. Well, that means that I see what happens when I plug in 0 to my composed function, and see what I get. Oh, it's a negative real number. That means that the principal branch will not work, but any other branch will. any other,
Any other branch?
yeah, any other branch, right? Because any other town, any other branch of this form, at least, right? We could conceive of a curve that comes out of here that happens to hit -2, right? Yeah, good point. Any linear branch, any branch that's defined by a ray will do. I could go out of my way and try to define some other crazy branch that happens to not hit the negative real axis at 2, but also I could just pick anything. I can pick anything other than this ray as a ray and get the job done, right? So, I get it, some people like to make things harder for themselves because it's interesting, but let's do the easy thing here. Let's pick some value of tau, okay, other than -pi, right? So, choose any value of tau other than -pi. What did I write here? Let's look at, for example, let's let tau equal to -pi/4. Okay, so this implies that our branch is given by L sub -pi/4 of z cubed minus 2, which of course is just equal to the real natural log of the modulus of z cubed minus 2 plus I times the arg sub -pi/4 of z cubed minus 2. Okay, so let's just draw a quick picture here. Okay, so here's -pi/4. Here's our branch cut, right? This ray. Okay, so we're looking at our domain is that looks kind of square. I meant for this to be parenthesis. Right, this is our domain for the branch, yeah? Or, I'm sorry, our range for the branch. Okay, so let's see what we get here when we evaluate this function at 0. L sub -pi/4 evaluated at 0 is just equal to oh, sorry. Right, I forgot that I am composing a function here. 0 cubed minus 2 is equal to the log of the modulus of -2, right? i.e. the absolute value of -2 plus I times pi. Right? Because here's my what, -2. What is the argument of this? That is to say, I should say, what is the argument sub -pi/4? Well, I'm going from -pi/4 all the way around to 7 pi/4, right? So pi is in that range. It's what we would expect for the principal value of the argument, right? It just so happens that we chose something that has the same value of the argument, despite our different choice of branch cut for the argument. Okay? Good? So, how about L sub -pi/4 prime? What do we get here? Sorry, I should write this in a different way, just so it's a little more transparent what's going on. First of all, let's write it up here. This is my branch, right? I want to take f prime of 0. This is d dz of L sub -pi/4 of d cubed minus 2. Okay, so evaluated at z equals 0. What's the derivative of script L sub tau in general? It's just 1 over z. It's just like the same as the principal argument. I'm sorry, the principal branch of lowercase log. The derivative is the same. It's defined by an equation of the same type, right? You can reproduce the proof in exactly the same way that we did it for an arbitrary tau, that L sub tau is analytic in some slit plane, in our case here, the plane that has the slit cut out here, and has derivative 1 over z. So again, we just use the chain rule. Right? So, we already differentiated this, right? Oh no, maybe we didn't actually. So, I get 1 over z cubed minus 2 times the derivative of the inside thing, 3z squared. Sorry, not minus 2. Evaluated at z equals 0. And what do we get here? Just 0, right?
Is that saying the derivative of arg is always 0?
That's saying that the derivative of arg is always 0. No. If that were the case, then we wouldn't be analytic, right? Because then the Cauchy-Riemann equations would fail.
So we can just ignore the arg in this case because
haven't ignored the R, right?
But when we were taking the derivative of L sub negative pi over 4,
Mm-hmm.
we don't consider the R, do we?
Well, so again, this is just the fact that the derivative of L sub tau is 1 over z is the same proof that we gave for the case where tau is equal to negative pi, right? That's the principal branch of lowercase log of z. That doesn't tell us anything about what arg is, what the derivative of arg is
So we
necessarily.
take the derivative of L sub negative pi over negative pi over 4 independently of what it's expressed as.
Yeah, the derivative is will be the same, no matter what the branch cut is.
Yeah, so like when we take the derivative, we don't look at the natural logarithm of the absolute value of, we just don't consider that.
Yeah, well, we don't take
Yeah,
derivatives component-wise
Yeah.
in general, right?
Yep.
This is this whole thing of analyticity, right? That the parts are bound, that we treat the complex number as a thing, a thing in its own right. Okay, good. Right. So, the important thing about this is that think back to when we talked about sine and cosine. The only zeros of sine and cosine when we extended them to the complex numbers were the real zeros. Now, just based on our investigation of the complex logarithm and choosing the principal branch of the complex logarithm, there's some analogous statement you might guess is true. It's like, oh, the values where the complex logarithm is not defined are the same as the values where the real logarithm is not defined. Negative real numbers, or sorry, non-positive real numbers. Not so. Right? You can define the complex logarithm of a negative real number. You just have to choose a different branch. Okay? So, branch cuts are tricky, right? They're tricky, but they help us, right? Because we can choose whatever branch we want when it's convenient for us. It's like, what's the log of negative n for a positive integer n? Well, I just choose some branch away from where that ray is, that lies on. Okay? So, multiple value functions are weird. But here's another thing to notice. Notice that no branch of lowercase log of z is analytic at z equals 0. Whereas, this is kind of what I was just saying, all other points of non-analyticity have some branch where they become analytic. Okay, so 0 is kind of special in this way. No matter what branch cut we make, even some crazy curve, I insist that 0 be excluded. And that is mainly just relying on the fact that the real part of the complex logarithm is based on the natural logarithm, which is not defined for 0. Yeah,
So when you say all other points of non-analyticity have some branch, it's every branch besides
That's
the
right.
ones that are just plus 2 pi of whatever we already were at.
Exactly.
Okay.
Yeah, there are many branches where some point of, take a given branch, any point of non-analyticity of that branch is analytic on almost all other branches. And you, as we were talking about before, you could construct some crazy curved branch that's not the same as the branch you started with, that happens to pass through that point, right? But almost all branches will restore the analyticity to that point. Okay? Good. Okay, yeah, so there's a name for this, right? So we call d equals 0 a branch point of log of z. This terminology sucks. I mean, branch cuts, branches, branches have two meanings, and now it's like, oh, a branch point. You mean a point on a branch cut? No, I mean a point that every branch cut contains. I don't know.
If we consider the extended complex numbers, then would infinity also be a branch point?
Good question.
You said that
Yeah, so remember, most often when we think of the extended complex numbers, it's for geometric or topological concerns. In terms of defining functions, yes, it's useful in certain cases, like for the inversion map. But we have not yet made an attempt to define what log of infinity is. This is a good question to think about. Can you define what log of infinity is? Well, it has infinite modulus. So kind of we would have to extend the real numbers and define what the natural log of infinity would be. I don't think that's typically done. It's not to say there's not something useful there, I just don't know. Okay. All right, good. So now, as I said at the beginning of class when we were discussing the midterm coming up, we're right at the doorstep of being able to say some really cool things about the integration of complex numbers. But there's some bookkeeping that we have to do beforehand. We have to discuss the sets which we want to integrate over, right? When we discussed integration, just as when we moved from real functions to complex functions, we spent a lot of time talking about the sets on which we define differentiability for complex functions, right? This whole unit on planar sets that we talked about, open and closed, etc. So now we have to do an analogous thing for integration. We have to determine what is the complex analog of an integral so that we can integrate against something, right? A complex function. That is to say, what type of set can we integrate a complex function against? That's our first task on the road to proving these really cool theorems about integration. Yeah.
If it's a multi-valued function in the complex plane, will it be a line integral of sorts?
So yeah, even when it's not a multi-valued function, it'll be a line integral. In general, it's a type of line integral.
Okay.
Yeah. Good. Right, so those of you who have studied physics or currently
I meant
studying...
multi-variable, yeah, that's...
Oh, okay, yeah.
It's like the X and Y, yeah. I switched up the terminology, we're talking about multi-variable.
That's quite all right. So yes, and what you say is exactly correct, right? So complex functions are multi-valued functions, and we'll be dealing with analytic functions, which are multivariable functions that have this extra condition of Cauchy-Riemann equations being satisfied. And so that actually gives us a lot more power. That's where all these cool things that we'll get to over the next couple of weeks come from. But first, let's talk about what is a curve. Okay? A curve, and I'll say in the context of something we can integrate over. Close parenthesis. Okay, so this is just going to be a bunch of definitions. And like I said, it's kind of bookkeeping, but you know, this will pay off in the end. It's how we will be able to keep track of what's going on. Okay. Okay. A set of points. We'll call gamma in the complex numbers is a smooth arc. If it is the image of some continuous complex valued function z of t, right? So here when I say complex valued function, what I'm saying is the output of this is a complex function, but my input, t, is a real number. So when I say complex function, I mean a function with a complex input and a complex output. When I say complex valued function, I mean a function that takes a real input and puts out a complex number. Okay? So in particular, where t is between a and b, some real numbers. Satisfying two conditions. One, z of t has continuous derivative on the closed interval a to b. Okay, and secondly, that z prime of t is not equal to 0 on all of the closed interval a and b. We can spot the mistake that I just wrote down here. Yeah.
It has a continuous derivative on the edges.
Yeah, exactly. In standard terminology, a function is never differentiable on the endpoints of its domain if the domain is closed. Right? What I mean by this is that, remember, the derivative is defined by a limit. And a limit exists if and only if the right hand and left hand limits agree. So when I discuss differentiability at the endpoints of this interval, a and b, for a, I am considering the right hand limit approaching from the right. And for b, I'm considering the left-hand derivative, approaching from the left. Okay, so as differentiable as you can be is what I mean when I say this. But that's annoying to write, so I just say this, the technically wrong thing and make some show of it. Okay? This will prove to make our lives a little easier later on. Because what we're going to do, what we want to do, the primary mechanism that will allow us to compute a lot of integrals is by taking concatenations of smooth arcs. We'll put them end to end. Okay? So this is why we have this wacky condition of being left and right-handed differentiable on the endpoints. And it'll just make it easier in the end. Take my word for it for now. Hopefully we'll all see that together soon. Okay, so.
Could you have a closed arc that isn't smooth?
Yes. Yes. So, there's only one theorem that we're going to discuss in this discussion of curves. And it says that any simple closed curve, I'm going to say this again on Tuesday, I'll just say it now. It says that the version that we'll state is that any simple closed curve divides the plane into exactly two regions. Okay. Now, ask me a question again. Say exactly what you said.
Could you have a closed arc that isn't smooth?
Right. Yeah. So this is the only way that we're going to use that theorem I just told you is the simple case when we're talking about smooth closed curves. But in fact, that theorem holds for arbitrary closed curves. And here's an example of a closed curve which is not smooth. In fact, it's nowhere differential. Okay, so here's a triangle. And on this triangle, I'll put triangles coming off each side of the triangle. And on each of these triangles, I'll put triangles coming off their open sides, the available sides. And on each of these, and I'll keep going, and then take the boundary of this set as I do it infinitely many times. This is a closed curve which is nowhere differentiable, therefore not smooth. But the Jordan curve theorem still holds. As I take the limit of drawing these triangles out to infinity, I still guarantee that I divide the plane into exactly two regions. Yeah, pretty crazy, right? Funny thing about this is called if you read about this on the internet, you can use this construction to create a curve that fills all of space. Pretty weird, right? Now, think back to section 2.7. Remember I showed you the Mentor sponge, right? So,
The one that contains all the curves.
yeah.
Okay.
So yeah. Well, no, this is contained in that thing. It's pretty crazy, right? Yeah.
Even if it contains all space?
Yeah. Yeah. Isn't that crazy? Yeah. Maybe I'll send some links out about that later. I'm gonna do some reading about that. Pretty cool.
I think I made too deep.
Yeah.
Go back to
right. Oh, I'm sorry, I didn't finish saying the conditions, there's an additional condition. Condition 3, is that my complex value function, z of t, is, 1-to-1. That is to say, what's the geometric interpretation of this third condition? My curve doesn't intersect itself. Okay? In we're essentially describing a parameterization, right? This is a parameterized curve, right? We have a real parameter t, and we're drawing a curve in the complex plane. Okay. So, additionally, we kind of jumped the gun on this. Gamma is called a smooth closed curve. If z of t is 1-to-1, sorry, 1-to-1 on AB, right? I intentionally leave this right endpoint out. And the value of z at A is equal to the value of z at B. And we also have their derivatives at A and B are equal. Okay, so just here's some schematic examples. Here's a smooth arc. Smooth arc. Non-smooth arc. Drew that pretty poorly. I wanted it to be actually a little smoother. I'll have to do smooth closed curve. Okay, now let me draw a non-smooth closed curve. What do I mean by smooth? Unfortunately, this is yet again another overloaded term. In this case, what I mean by smooth for this class of curves that I'm describing is that it makes sense to define a tangent line at each point on the curve. Right? So here at this point of self-intersection, is my tangent line this slope or this slope? There's no reasonable way to tell. I can't know that. This is a smooth closed curve because I insist that the derivatives agree at this point where it meets itself again. Okay? Whereas here is my tangent line this or this. Again, there's no reasonable way to tell. And so that's this whole business of smoothness, is that I can define a tangent line at each point to the curve in a non-ambiguous fashion.
So are the only points where you might lose smoothness when it intersects itself or it connects with itself?
Yeah, so under these conditions, right?
Yeah.
I'll have continuous derivative everywhere and non-zero everywhere. Yeah, and one-to-oneness is what makes sure it doesn't intersect itself, right? That every t value has a unique. No, sorry, I didn't mean to say that. That if z of t1 is equal to z of t2, then t1 has to equal t2. Whereas, so really when I think about parameterization, remember I'm thinking of like, okay, here I start at t is equal to 0, say, or a. And then I go, I get to a plus epsilon, say. And then I keep going, and I get a plus delta, where delta is greater than epsilon. I have two distinct values that map to the same point. That's why we insist on one-to-one, so we don't intersect ourselves. Okay.
And the smooth closed curve is fine because it's parenthesis on B instead of a.
Yeah, exactly. So we insist that it's one-to-one, so the only point it intersects itself is where it just meets itself. And we guarantee that the derivatives behave nicely there. Okay. Yeah?
Looking ahead of it, is there it's like Green's theorem applies for closed curves in R2?
Simple closed curves, right?
Yes. And is there some property that we can use with the Cauchy-Riemann equations to make something interesting happen? Using Green's theorem?
Depends on what you mean by interesting.
Is there some nice property that we can exploit?
Why don't we continue and see what we see? I'm not sure the answer to your question. I mean, I like where you're going here, but I just simply don't know at this point. We're a long way away from Green's theorem in my calculus 3 class right now, so I haven't really thought about that since I taught it last fall. So maybe there is something there, I'm not sure. Okay. So, for our purposes, we're mainly going to just parameterize lines and segments of arcs of circles. Those will be the main smooth arcs and smooth closed curves that we'll be concerned with. But it's good to see this stuff in general. Like you see the full power of it, right? Okay, so okay. Our definition of smooth arc and smooth closed curve guarantees parameterization exists of said objects. But of course, the parameterization is not unique, right? I can come up with many different parameterizations of the same, for example, smooth closed curve, right? But not a unique one. Let me give you a parameterization, and you tell me how to draw it. What if I say z1 of t is equal to cosine t plus I sine t. what is this parameterized? Oh, I didn't tell you all the information. For t in 0 to 2 pi. What is this parameterized?
The unit circle.
Unit circle, yeah. And in particular, what way does it parameterize it? Yeah, in the
So anti-clockwise.
yeah, in the standard way, right? How we usually think of the unit circle, we record angles going counterclockwise. Right? I'll put an arrow there. How about V2? If I plug in, V2 is T. If I have a negative on my T, negative T. Well, remember that cosine is even, so this is just the same as cosine T, minus, and sine is odd, I sine T, right? This is also a parameterization of the circle, but I draw it differently, right? Oh, sorry. Where T is between 0 and 2 pi. And I'm taking negative y values. Yeah. Okay. Let's do one more. One more different parameterization of the circle. The unit circle, I should say.
Would it be a different parameterization to cosine t plus 2 pi? Right? T plus 2 pi?
Technically, yes.
And then they kind of condense into one.
Yeah, I mean, it depends on what you mean by different,
Yeah.
right? It's oriented the same way, and you get the same thing. Maybe this will answer your question. What we consider different parameterizations. What if I take z sub 3 of t equal to cosine of 2t plus I sine of 2t for t in the half open interval 0 to pi. How does this parameterization of the circle look like? Start here at t equals 0. It happens faster, right? So we scale this and shrink our domain. Okay, so this is a different parameterization. Again, it looks exactly the same as this. It has the same orientation.
The only reason why I'm saying questioning is because cosine t plus 2 pi, like that, an identity says that's the same thing as cosine of t.
Right.
So would even, like, would that, I guess it would change it if you put, because you could do like from 2 pi to 4 pi then, but that's kind of,
Yeah, so I
like,
think
what wins, the identity for cosine or the parameterization?
well, I think the takeaway answer is that anytime you have a different expression for what you wrote and a different domain, it's a different parameterization. Even though it looks the same, it's still different. Right? Like if you didn't see me draw this, there's no telling the difference between this and the first one. Z3 and Z1. Okay, so this kind of points to what something we'll need to do. We need to account for this directionality in our parameterization. Account for the directionality for orientation. our parameterization. By introducing a directed smooth closed curve. Okay? That is to say, I take a smooth closed curve and I just put a direction on it. There's two choices, right? You go, this is a modification of the right-hand rule. You have some smooth closed curve, you curl your fingers in the direction that the arrow goes, and if your thumb points out, you're positively oriented. Right? In this case, I curl my fingers in this direction, and my thumb points in. That's negatively oriented. So it's obvious with the unit circle, right? Because this is our convention. These are positive angles when we go counterclockwise. But I may have something really crazy, right? And I put an arrow here. It's like, let's see. Oh yeah, look, that is counterclockwise. My thumb points out. Okay, so it's this is where Green's theorem comes in, right?
That is in two-thirds.
Yeah, right. So, or I guess actually it's
That's Stokes' theorem, right?
right. So Green's theorem, Stokes' theorem recovers Green's theorem.
Yeah.
Right.
Two dash,
And having that cross product is where you see why that counts as positively oriented, because then you actually see the right-hand rule. I'm just talking calculus 3 here, just because I'm going to have to teach this to people that see it for the first time relatively soon. But in any case, I think we understand this whole convention, right? Okay, good. Okay. So we're I would say more than halfway there for our bookkeeping mechanisms for the things that we want to integrate over. Our only remaining piece here is to say that we can stitch together smooth arcs that have endpoints that match. Okay? So let me just say, we can stitch. Is there 2 T's in stitch?
Yeah.
Yeah? Okay. Stitch together. Sorry, directed. Smooth curves. In a compatible way. By the following definition. A contour capital gamma. I think this was the first time that I encountered a capital gamma. Maybe you all have seen this before, but when I was an undergrad and I took complex analysis, I think this might have been the first time I actually looked at a capital gamma.
Stats.
Say again?
Profit stats.
Say again?
Like probability statistics, like the gamma.
Oh, I never took probability in statistics. So maybe that was my fault. So a contour gamma is either a single point or a finite sequence of directed smooth curves gamma 1, gamma 2, up through gamma n. Such that the terminus of gamma k is the initial point of gamma k plus 1. For k equal to 1 up through n minus 1. And we write capital gamma equals gamma 1 plus gamma 2 plus gamma n. And so this plus operation isn't addition in any conventional sense. It really just means concatenation. We just stick them together. Okay, but we're running out of time here, so I'll just say this. This notation of adding together directed smooth curves is very handy when we start to integrate over contours, because it'll turn out that when we define contour integrals, they're linear over contours. We can split the contours up into their directed.
Same thing in Calc 3, right?
Yeah.
Yep.
Yeah, exactly. Okay, so I think that's all I should say today. We'll pick up there on Tuesday, and I'll shortly send out well, probably tonight sometime, a few hours from now, I'll send out a message asking if we really think we should postpone the midterm. I think we should, but have a good weekend.
You too.